In computer networks, we are discussing chapter number 2, the physical layer. Balanced signals. Bipolar AMI encoding. What is balancing? Balancing means positive and negative voltage equally. That is a proper mix of positive and negative voltages. So this balancing helps to provide transition for clock recovery because there is a mix of positive and negative voltage. If the signal is unbalanced, that is more positive or more negative, average may drift away from the true decision level. There may be densities of 1, right? For example, this unbalanced signal may cause more symbol to be decoded with errors. So the balanced code, what do? We use 2 voltages to represent 1 and 0. In a balanced code where there is a proper mix of positive and negative voltages, we use 2 voltage levels. For example, the plus 1 volt we are using say for 1 bit and a negative 1 voltage for 0 bit. This is how it will be balanced also, and we will be able to represent a 1 and 0. In order to send a 1, for example, the transmitter will alternate between the positive value and negative value, that is the plus 1 here and negative 1 voltage levels, so that because of the balancing, they always averages out. Okay? So this is alternating. The transmitter will alternate between plus 1 and minus 1, and this scheme is called bipolar encoding. If you talk about telephone network, it is called as AMI or alternate mark inversion. Bipolar encoding in telephone network is AMI, and in AMI alternate mark inversion, 1 will be called as mark and 0 will be called as a space. How does it work? See, 0 we are going straight, 1 there is a height, then 0 again we go like that, but again 1 is coming, so we alternate. We don't go up, we go down. That is, plus 1 was there, now we are going to negative 1. Again there is an inversion because 1 is coming, so we have to invert it. Then 1, again we are going down, and then 0 it's straight. So this is bipolar AMI encoding. Bipolar encoding, or all these encoding we are discussing, it adds a voltage level, because in order to achieve a balance, there has to be some voltage level to be added, as done in bipolar encoding. We don't want more 1s or more 0s. So we can use a mapping like 4B and 5B to achieve this balance. We have already seen this. Okay, this will help in a transition for clock recovery also. So here we can use 8B and 10B. So 8B, 10B line code, how does it work? 8B, 10B, the 8 bits of input, they are mapped to 10 bits of output. 8 bits of input in 8B, 10B, 8 bit is the input and 10 bits are the output, so they are mapped. The 8 bits, how does it work? See, there is 8 bit, so this 8 bit, they are split into 5 bit, a group of 5 bit and a group of 3 bit. This first 5 bit will be mapped to 6 bits, and the next 3 bit will be mapped to a 4 bit, and this 6 and 4 will then be concatenated or they will be combined. So in each group, some input patterns, they can be mapped to balance the output patterns that have the same numbers of zeros and ones, because this is all about balancing, right? That is why we are using 8B, 10B. For example, 0001 is mapped to 1001. 001 we have 2 zeros and 1 1. So it is not balanced. But we have mapped it in 8-bit NB to 1001. 2 ones, 2 zeros. So it is balanced now. That is why we are using 8-bit and 10-bit for balancing. But since we don't have enough combination for all the output patterns in order to balance it, because we need equal number of ones and zeros. So each input pattern will be mapped in this scheme to 2 output patterns. One will have an extra 1 and the alternate will have an extra 0. So there will be 2 alternates. I'll show you an example. Now you see here, this is the map. 0 0 0 is mapped to 2. That is 1 0 0 1 0 1 1 and 0 1 0 0. Now since we have mapped it to 2, and what are these 2? These are 2, but these are 2 nothing but the other one is the complement of other. That is 0 1 0 0 is there because 0 0 is mapped to 2 values, and this 0 1 0 0 is nothing but the complement of 1 0 1 1. So which one will be used? Your question will be 1 0 1 1 will be used or 0 1 0 0 will be used. This will be assigned. How? Because as the input bits are mapped to the output bits, the encoder will recall the disparity from the previous symbol. Now you will ask question, what is disparity? Disparity is the total number of zeros and ones by which the signal is out of balance. You just need to calculate or compute how many ones are there, how many zeros are there. Take the difference, you will know that, oh, this one, there are ones higher, there are zeros more. Okay, so if you have 2 and 3, you just take subtraction 1. So 1 is out of balance. 1 is out of balance if there are 2 ones and 3 ones. So the encoder will select either an pattern, output pattern, or the alternate. It may use 1011 for 000 or it may use 0100 for 000. I hope you got the idea, because it has to reduce the disparity. With this 8B and 10B, the disparity will be at most 2 bits. That is, the signal will always be balanced. And there will be never ever more than 5 consecutive ones or zeros. If you take any combination, put them in any way, you will not get more than 5 ones or 5 zeros. Pass band transmission. So in order for the wired transmission, the communication over these baseband frequencies are most appropriate. For example, the twisted pair, the coaxial cable, or the fiber. So for these wired transmission, communication over baseband frequencies are mostly used. But when you go to wireless networks and the radio transmission, here we use a range of frequencies, because here they will not start with 0. Okay, so there will not be baseband frequencies here. For wireless channels, when you are using different frequencies, the antenna size will be different. Because if you are using very low frequency signals, the antenna size will be impractical to be made, because the antenna needs to be a fraction of the signal wavelength. Now how do we prove it? Let us take an example, because the antenna size is of the idea of these frequency. So wavelength and frequency. Now let me tell you that which becomes large at higher frequencies. Okay. Now we have an example here. We have a frequency 15 kilohertz. Now with all the calculation, the lambda equal to C equal to nu lambda and lambda by 4, the size of the antenna becomes 5 kilometers. So this is just to give you an idea that the 15 kilohertz frequency will want you to have an antenna of 5 kilometers. Even for the wires, when I'm talking about wire also, placing a signal in a particular frequency band is useful, because that will allow different kind of signals that can coexist in the channel. Passband transmission. So passband transmission is all about arbitrary band of frequencies, different bands of frequencies. Band means the range of frequencies which is used to pass the signal. So the frequency band can be anything. This can be a band, this can be a band. So that is why we are saying arbitrary different band of frequencies which are used to pass the signal. This is the passband transmission. It is a range. Means arbitrary band means different band, different frequencies and different range. These are used to pass the signal. So what we can do is, the best way is to take a baseband signal. We know that it goes from 0 to some B hertz, if B is the bandwidth, and you can shift it up to you can shift it to S, shift by S. So when you shift it by S, the passband of S, that is, it will become, now when you shift it from S, just add S. So S till S plus B, it will, because you are not changing the amount of information it can carry. You have just shifted it, this baseband signal. But the signal might look different. What will happen at the receiver end? We can shift this back, what we have shifted to S plus B, again we can shift it back to B, that is again to 0 to B, back to the baseband, and in this baseband it is more convenient to detect the signals. It is very easy and convenient to detect signals, that is why we are shifting it back. This can be done. So the digital modulation, because in passband transmission, that is digital modulation is accomplished with this passband transmission by modulating the carrier signal that sits in the passband. So the modulation is all about bits to signals and signals or to bits to analog signals and then back. So we can modulate or change the carrier signal that sits in this passband. This is how passband transmission, digital modulation is done. So what I am trying to suggest here is, we can modulate either the amplitude, the frequency or the phase of the carrier signal. These are all the properties of any wave, carrier signal. So the amplitude change, frequency change or phase change or variation, this can be employed for actual digital modulation, right? ASK or amplitude shift keying. Here, the way of digital modulation, two binary values are represented, that is may be 0 or 1, they are represented by different amplitudes of the carrier frequencies. What is the amplitude? Amplitude is the distance from the base level, how high the trough is or the crest is. So the amplitude for 0 can be like this, and for 1 it can be like this. So the change in amplitude will reference different bits, different binary values. Okay. So changing the amplitude, we can represent different binary values. Okay. The problem here is in ASK, it is quite susceptible to noise and people regard it as not that efficient modulation technique. And this is used for up to 1200 bit per second on the voice grade lines, that is the telephone lines called, and very high speeds over optical fiber. ASK. Let me tell you more about this. This is your bit stream. The main idea, we are trying to modulate. We are changing these bits to signals. So this is the carrier wave. It has a frequency, it has an amplitude, it has a phase. So how to represent it using the amplitude? So wherever you see 1 here, only that will be output. wherever you are seeing here, there will be no amplitude. You can say amplitude is 0. You can even reduce the amplitude, that can be done. But here you see no 0, no amplitude. In everywhere 1 you will see this same wave. 0, you will not say any wave. That is the amplitude will decide. This is the amplitude shift keying. So in amplitude shift keying, two different amplitudes are used to represent 0 and 1. More than 2 levels can be used to encode multiple bits also per symbol. For example, in one symbol you can send 0 0. You can send 0 1 0 like this. FSK or frequency shift keying. FSK. This is also a digital modulation technique. So here we have carrier wave, and the frequency of the carrier signal or wave is varied or changed to represent binary 1 or 0. One frequency will show 1, the different frequency will show 0. Both peak amplitude and the phase will remain constant. Only we are talking about frequency changes here. The frequency of the signal during each bit duration will be constant. It may represent a 0, it may represent a 1. Frequency is what? Number of oscillations per second. For example, this is the range. Now I can make a wave like this. In the same range, I can show the wave like this. So one is having the low frequency, the other one is having a high frequency. So one may represent say 0, the other may represent a 1. Now see here, you have the amplitude and phase are not changed, but when you have a 1, the frequency is higher, the number of oscillation or the number of waves are higher. So all these higher frequencies will represent a 1, but when it comes to 0, the frequency is less. It will represent a 0. So the frequency shift keying, 2 or more different tones are used. You can also say frequency or tones. So now you see a picture here. This is again an example. This is a bit stream. Now we have two carrier waves, high frequency carrier wave. This is very high frequency, number of oscillations are higher, and the low frequency carrier wave, number of oscillations per second are less. When you do the FSK, whenever 1 will be shown, high frequency will be shown. Whenever 0 is there, the low frequency will be shown or will be sent to the receiver, and that is how it deciphers it. Phase shift keying, PSK. Phase means angle. So when we change the angle of a wave and then represent 0 or 1 bits, binary digits, this is called PSK or phase shift keying. In phase shift keying, the phase of the carrier wave is varied, changed to represent 2 or more different signal elements. Remember, the amplitude and frequency will remain same. If you're talking about binary PSK, we will have only 2 signal elements. One signal element with a phase of 0, angle of 0. The other one will have a phase of 180 degree. Let me show you. This is the Cartesian coordinate system. You are already aware of it. Now a line x-axis, if you make a line on x-axis, that will make an angle 0 with the x-axis. But a line which is opposite to the x-axis will make an angle of 180 degree with the x-axis. So the first one can be made to represent a 0. The second one can be made to represent a 1. So this is a constellation diagram. You'll see it in QAM 16, QAM 64. So bit 0 will have a phase of 0. The receiver, whenever it will have get a phase of 0, will say 0. If it gets a carrier wave with phase 180 degree, it will regard it as 1. So phase shift keying, the carrier wave is shifted 0 or 180 degrees at each symbol period. And because we have 2 phases here, it is called as BPSK or binary phase shift keying. So binary, we are referring to the two symbols, not that the symbol represents the two bits. Okay. So these are PSK and BPSK. But there are better schemes also. There are better scheme like QPSK. First let me tell you about this. Now if you want to send a 1, it is like this. But whenever you want to send a 0, there will be a phase shift. You see there is a phase shift of 180 degree. So this is how 0 will be represented. Again you have a 1 after that. So there will be a phase shift. This is a phase shift. Again you go, but from 1 to 1 there will be no phase shift. Again from 1 to 0 there will be a phase shift. 0 and 180 degree. So this is how 1 and 0 will be represented. So I was telling you about the QPSK. Now again going to the Cartesian coordinate system. So 0 and 180 degree we saw. Now let us make a line here in between. We can represent 4 angles because the waves have different angles, 0 to 360 degree. So you can represent 45 degrees from x-axis. This angle is 135 degree. This angle from positive x-axis is 225 and this whole angle is 315 degree. Now this scheme is QPSK. We are using 4 different angles. That is, these are, one can be used for 0, 0, second can be 0, 1, third can be 1, 0, fourth can be 1, 1. So this QPSK is quadrature phase shift keying that uses the channel bandwidth efficiently to use 4 shifts, 4 angles, 45 degree, 135 degree, 225 degree, 350 degree, and here we are transmitting 2 bits of information per signal. Okay. Binary 2, quadrature 4. In binary we can send only 0, 1. In quadrature we can send 0, 0, 0, 1, 1, 0, 1, 1. We can combine this ASK, FSK and PSK, amplitude shift keying, phase shift keying and frequency shift keying. These schemes can be combined and we can use more levels to transmit more bits per signal. That is not only 0, 1 but 0, 0, 1, 1 or 0, 0, 0, 0, 1 like this. See, frequency and phase, they are related. So only one of them, either frequency or phase, can be modulated at a time because they are related, because frequency is nothing but the rate of change of phase over time. So either you can take phase or frequency. Let us say we are taking phase. So the amplitude and the phase, these are modulated in combination. You know why we are not using frequency? Because only one can be taken. But phase is, this amplitude is different. So in this figure, if you see, we have 4 dots. These 4 dots are equidistant and at an angle of 45 degree from the positive x-axis. This is 45 degree. What is the angle of this second one on the second quadrant? It's 135 degree. In the third quadrant, 225 degree. Fourth quadrant, 315 degree. So now we can represent four symbols. So that symbol can be 2 bits because 2 to the power 2 is 4. Okay. So the phase of a dot is indicated by the angle a line from it to the origin make it with the positive x-axis. The phase is like this. The amplitude of the dot is the distance from the origin. Now this kind of diagram, you see dotted diagram, this is called a constellation diagram. So now in A you see 4 dots, in B you see how many dots? 14. So as I said, here 2 to the power 2 is 4. So at the same time you can send 2 bits per symbol, 0, 0, 0, 1, 1, 1, 1, 0. In this 2 to the power 4 is 16, you can send 4 bit at a time per symbol, like 0, 1, 0, 0 you can send, 1, 1, 1, 0 you can send. 16 combinations are there. So 16 combination, not only about phase, but we are combining the amplitude and the phase I used here. So the modulation scheme can be used to transmit 4 bits per symbol. 4 bit. Okay. This is called as QAM16 or quadrature amplitude modulation. QAM16. How does it work? See here. Now let us say we have A as some distance. A can be 1 by root 10. So once we want to send 0101, what is the angle? 45 degree. So the phase will be 45. As I said, we are taking the combination of phase and amplitude. What will be the amplitude? The amplitude will be the distance of 0101 dot from the origin. Let us say it is A. Okay. So once we want to send 0101, this will be like this. Now we want to send, say, 0010. What will be the angle? What will be the phase? The phase will be, now let me just join it. From positive x-axis it is 135 degree. So it will be 135 degree, and amplitude can be, you can take the distance, it can be, say, 3, taking an example. So these are the combination. For every bit, for every bit combination, 4-bit combination, there will be a proper pair of phase and amplitude. This is called QAM16. Now the third figure you see. This figure is more denser. First one was having 4, then 16, then we have 2 to the power 6, which is 64 dots. So we can have 64 different combination of amplitude and phase. Now we can say send 6 bits per symbol. This bit combination, one of the combination I said. This is called as QAM64, quadrature amplitude modulation 64. 6 bits can be transmitted per symbol because we have 64 different combination of amplitude and phase. Amplitude, distance from the origin, phase is the angle from the positive x-axis. Okay. Now how do we assign the bits? You can say how these bits are being assigned. Why we have 1111 here, 1011 there? Why can't we have some other combination? Okay. You can have 1000 at the top. Why can't you have it in the third quadrant? The main argument is, the important consideration is that a small burst of noise at the receiver may not lead to many bit errors. So assigning consecutive bit values to adjacent symbols, that is what we do. For example, in say QAM16, let us take the example of the second figure. If one symbol, say it is 0111, and the neighboring symbol is, for example, 1000. If the receiver mistakenly picked the adjacent signal, the whole bit sequence will be wrong. So the solution is, we assign the adjacent symbol so that they only differ by 1 bit. That is the gray code. Gray code is when two combination, they only differ by 1 bit position. That is called the gray code. So you see here we have an example. This figure shows QAM16 constellation gray coded. Now these combination all have only 1 bit as differ by 1 bit, gray coded. Okay. Now if the receiver decodes the symbol in error, it will make only a single bit error because of the gray code. Multiplexing. This we are going to see in the next discussion. Thank you so much.